All right, well, welcome. In this video, we're going to be looking at how to graph rational functions, and we're going to do this by hand. And so before we get started, we need to first understand some different graph properties. So let's look at that first graph property, and that's this idea of a hole in a graph. Now, this is a discontinuity that's called a removable discontinuity. And so or another name that we call it is a hole, and that occurs when you factor the denominator and it cancels with the factor in the numerator. So let's look at this first example. Here we have x plus 2 divided by x squared plus 5x plus 6. Now the denominator isn't factored, so we want to get that denominator in factored form. So I'm going to look to find two numbers that multiply together to be 6 that add together to be 5. And so those two values would be 2 and 3. So I'm going to factor this down to be x plus 2 times x plus 3, because 2 times 3 is 6 and 2 plus 3 is 5. Now if you notice, in the numerator we have a factor of x plus 2, and the denominator we also have a factor of x plus 2. So that means we're going to have a hole where x equals negative 2. Now we want to make sure, so now this hole is a coordinate. And so I want to figure out, well, what's the y value for this coordinate? So to figure out what that y value is, we're going to take the simplified form. So this fraction, we would have the numerator cancels out. So we're left with 1 over x plus 3. So to find the y value, we're going to replace negative 2 in here for x. And if I simplify that, I would get in the denominator negative 2 plus 3 is 1. 1 divided by 1 is 1. So again, this is giving us the y value. So when x is negative 2, the y value would be 1. So in other words, the hole is at the coordinate where x is negative 2 and y is 1. So that's how you identify where a hole would be in your graph. And again, that occurs when you have a factor in the numerator that cancels out a factor in the denominator. All right, so that's our first graph property we need to talk about. The second one is going to be this idea of a vertical asymptote. So if we have the numerator and the denominator in factored form, a vertical asymptote is going to occur when you have any factors that are left over in the denominator if we can't cancel them out with the numerator. And we call this a non-removable discontinuity because, again, it doesn't get removed. It doesn't get canceled out like we did with the previous example. So let's look at this first example here where we have 2x in the numerator. The denominator we have x squared plus 5x plus 6. If you notice, it's the same denominator that we had before. So this would be the same as 2x over x plus 2 times x plus 3. And nothing can cancel out here. We don't have any common factors between the numerator and the denominator that cancel out. So that means that both of these are going to be what we call non-removable discontinuities in our denominator. Because remember, we've talked about this in the past where we said that our restrictions in our domain is that x can't equal negative 2 and x can't equal negative 3. So the way that those look in our graph is that those would be vertical asymptotes at those points. And so we represent a vertical asymptote as an equation. So we'd write these separately. So we would have the equation x equals negative 2 would be a vertical asymptote, and x equals negative 3 would be another vertical asymptote. So let's tie both of these examples into this next, or both of these properties rather. We're going to tie those properties together with this next example. So let's factor that denominator. So the numerator would stay x plus 1 for right now. And if you factor the denominator, you would get x plus 1 times x minus 2. So we're trying to find what two numbers multiply together to be negative 2 that add together to be negative 1. And that'd be 1 and negative 2. All right, so now when we go and look at this, you should recognize that the x plus 1 and x plus 1, those would cancel each other out. So it means we're going to have a hole where x equals negative 1. So I need to figure out what would be the y value when x is negative 1. So if I put negative 1 in here for x, we would have 1 in the numerator. And the denominator, negative 1 minus 2 would be negative 3. So we would have a hole where x is negative 1 and y is a coordinate negative 1/3. All right, now you notice in the denominator we have that x minus 2 that did not get canceled out, that did not get removed. So that means we would have a vertical asymptote where x equals 2. Because if I set that equal to 0 and solve it, we would get the equation x equals 2. So those would be our two key properties for that particular function if we were to graph it. So we'd have a hole at one coordinate, and we'd have a vertical asymptote at x equals 2. All right. I want you guys to go ahead now and try both of these examples. So this first one, the denominator has been factored for you. And actually, you know what? Before we let you guys loose on this one, let's review how to factor when the a value isn't 1. And so let's look at that second one. We'll get that one factored down first, and then I'll have you guys try that one on your own. So you got to remember, if we have an a value that isn't 1, what you can do to factor that down is you multiply those first and last terms. So I get negative 12x squared, and my middle term is x. So I'm trying to find two values that multiply together to be negative 12x squared that add together to be 1x. And that would be negative 3x and 4x, because negative 3x times 4x, sure enough, is negative 12x squared, and negative 3x plus 4x is 1x. So we're going to leave that 6x squared, but in the middle, I'm going to replace x with negative 3x plus 4x. We have the minus 2. Then from here, we're going to factor this by grouping. So we're going to group together first two terms and the last two terms. So in those first two terms, yes, they both have an x, but they also are both divisible by 3. So we factor out a 3x, leaving us with 2x minus 1, because negative 3x divided by 3x would be negative 1. In the next set, whatever sign is here, remember we bring that down, so that would be a plus. And between 4 and 2, the GCF, the greatest common factor, would be 2, also leaving us with 2x minus 1. So the factors that are the same there are 2x minus 1, so it's going to be one of my factors, and then what's outside of here is your other factor, 3x plus 2. So this would be the same as 2x minus 1 over 2x minus 1 times 3x plus 2. All right, so now I want you to pause the video, and I want you to find any particular properties between holes and vertical asymptotes for both these examples. So pause the video and hit play when you're ready to check to see if you got it correct. All right, let's look at that first one. So that first one, you notice that there's nothing that cancels out between the numerator and the denominator. So we have two vertical asymptotes. I'm just going to call it BA to make it easier. So we would have one vertical asymptote at x equals negative 5. We'd have another vertical asymptote at x equals 4. And yes, you do need to write them separately like that because we're writing them as equations. Because when you go to graph that, that would be a vertical line. So like we'd use a dashed line at x equals negative 5 and a vertical dashed line at x equals 4. And yeah, so those are your only properties for that first one. Let's look at the next one. So the next one, we can see that, yes, the 2x minus 1s cancel each other out. So that means we're going to have a hole where x is, because if we set that equal to 0, we would get 1/2. So then to figure out what the y value would be, I'm going to put 1/2 in here for x. So this gets a little ugly, so let me show you how we would simplify that. So 3 times 1/2, that would just be 3/2. Now I know the 2, I'm going to have a common denominator to be able to add these two together. So I'm going to change that 2 to be 4 over 2. So then we would have 1 over, then the denominator we would have 7/2. So using that idea of keep, change, flip, to simplify this, we would end up with 1 times, flip that denominator, so we would, so we would have 2/7, which would be 2/7. So I know that gets kind of ugly, but you do want to make sure you know how to work with fractions, because this will happen, and we would not want to use a decimal there because it would not be a nice decimal that terminates. So we'd want to make sure that we're exact by leaving it as a fraction. So if you need to pause and kind of reflect or go back and re-listen to what I just did, make sure you do that, because you want to make sure you know how to simplify a fraction. All right, so now we do have a non-removable discontinuity there with a 3x plus 2. So if I were to set that equal to 0 and solve it, we would have a vertical asymptote at x equals negative 2/3. So those are what we would call our discontinuities there for those two examples. All right, so if you look at that bottom section of your notes, so the next part of your notes, We're going to be talking now about some other types of asymptotes. So we've talked a lot about vertical asymptotes. Remember, we write those in the form x equals a number, and we just did that in those previous examples. But there's also other asymptotes that could be horizontal or oblique, or what we would call slanted asymptotes. Now, before we talk about what's in this box, I really want to make sure that you catch what this box is saying here, or what's above the box. This is how we're going to start these out. We're just going to focus on the leading terms, okay? And we're going to take the leading terms between the numerator and the denominator and reduce those. So in this first example, the leading terms are 2x squared. That's not showing up very well. Whoops. Hit the wrong button here. All right. So the leading term in the numerator would be 2x squared. So what's the leading term? It's the term with the largest exponent. So the leading term in the numerator is 2x squared. The leading term in the denominator is 5x to the fourth. So I'm just going to look at that as a fraction. What we're going to do is we're going to reduce that. So 2/5, I can't reduce anything from that. But here we would have x squared, so it means we have 2x's in the numerator. That's going to cancel out 2x's in the denominator, leaving us with 2 over 5x squared. Now, I call this is what we call bottom heavy. Oops, let me rewrite that. So what I mean by bottom heavy is that the denominator has a bigger x. So we have the larger x, we have x squared. We don't have an x in the numerator, but after we're simplifying it, we have our variable in the denominator. So it's what we would call bottom heavy. So if that happens, that means we're going to have a horizontal asymptote at y equals 0. Okay, so this one would have a horizontal asymptote at y equals 0. Now let's look at this other example. So here again, we're going to have our leading coefficients, our 4x squared, and 2x squared. Let's reduce that. Now here the variables completely cancel out, leaving us with just 2. So if that happens, if the x's cancel out, there's a horizontal asymptote at y equals whatever is left over. So y equals a number. So in this case, it'd be y equals 2 would be our horizontal asymptote. And so this one again, they cancel out. So if that happens, you're left with just a number. So we would say it's y equals 2. Let's look at this last one. If x's are left over in the numerator, then we're going to have a slanted asymptote. And we're going to divide using long division or synthetic division, or we can even use the box method. Remember we talked about the box method earlier this chapter. And we ignore the remainder. So if there's a remainder left over, we don't care about it. We just want to figure out what the answer would be if we were to divide those out. So this one, we would have 4x cubed in the numerator, 2x squared in the denominator. So this one is what we would call top heavy, because there'd be an x left over in the numerator. So it doesn't matter that there's an x left over in the numerator as far as what that means for our answer. The only way to figure out where would that slant be, or what would be that slant asymptote rather, or oblique asymptote, is we would divide these. So remember, I'm going to use the box method for this. Actually, I'm going to put 0x in here, plus 3. All right, so we're dividing by 2x squared plus 3. And I'm just going to rewrite the 4x cubed plus 2x minus 1 down here. So if you remember the process is that we take whatever this first term is, put it up here in this box. And we ask ourselves, okay, what would I multiply 2x squared by to get 4x cubed? Well, that would just be 2x, because 2 times 2 is 4, x times x squared would be x cubed. So we get 4x cubed there, so now we're going to fill this in. So 2x times 0x, that would be 0x squared. 2x times 3, that would be 6x. All right, so now we don't care about the x squared term, because if you notice, the x squared terms add together to be whatever our x squared term is in our original polynomial. And we don't have an x squared term, so if we want to do, we could put 0x squared in here. And so that means that this would be just 0. Okay, because 0 times 2x squared would be 0x squared. If I fill this in, I'd get 0x, and I would get 0 here. Now, if you notice, this represents our constant. So that means anything left over would be a remainder. And we don't care about the remainder here. So what that means is that our oblique asymptote, our slant asymptote, would be the equation y equals 2x. All right, let's put this all together, everything we've talked about, into this next example. So there's going to be a lot to this example. I'm not going to squeeze it all in on this one slide, but I just want you to see that we're going to do A through H here. So the first step is we're going to write this in factored form, and then we're going to use that factored form to find, I'm going to first, I think would be first to be good to talk about holes and vertical asymptotes, and then we'll use that to figure out what the y-intercept or what the x-intercepts and y-intercepts would be. And I'll talk about why that is here in just a minute. All right, so let's start by writing this in factored form. So in the numerator, we have a situation where the a value is 2, it's not 1. So I'm just going to do this work over here. So we would multiply these two together. And so I'm just going to write that down as negative 10x squared. My middle term is 9x. So we're trying to find two values that multiply together to be negative 10x squared that add together to be 9x. So did you come up with that? Well, that's going to be negative x and 10x. Those multiply together to be negative 10x squared and add together to be positive 9x. All right, so I'm going to rewrite the 2x squared. And then I'm going to write minus x plus 10x. By the way, it does not matter what order you write the minus x and the 10x. If you switched them around, you'll still end up with the same answer. And then we put the minus 5 there at the end. And then we're going to factor this by grouping. So those first terms, first factors there, or first group, factor out an x, giving us a 2x minus 1. Next group, write down a plus, and then those are both divisible by 5, leading us with 2x minus 1. All right, so now we would have first factor is 2x minus 1. The last factor would be x plus 5, or you could have the factors in a different order. So that's my numerator. And the denominator, well, we just have an a value of 1. That makes it real easy. So we're trying to find two numbers that multiply together to be negative 20, that add together to be 1. And that would be x minus 4 and x plus 5. All right, now I know it says to find the x-intercepts next. And we get the x-intercepts by setting the numerator equal to 0. So we would basically take the factors, set them equal to 0, and solve it. But this, get a different color here, this is not going to be an x-intercept or a 0. The reason why is because that cancels out with our x plus 5. So that is actually a removable discontinuity. So that means that's going to be a hole in our graph. So let's skip over to where it says find any holes. So we're going to have a hole. So at that, so again, when those x plus 5s cancel out, we're going to have a hole where x is negative 5. Because remember, you find that hole, you set that factor that canceled out, set it equal to 0 and solve it. So we get an x value of negative 5. And to find out what our y value is, now this one's a little different, we're going to put negative 5 in for x. Now we have two values, though, to put 5 in for x. So let me do that work over here. So we'd have 2 times negative 5 minus 1 in the numerator. And the denominator, we'd have negative 5 minus 4. So in the numerator, 2 times negative 5 is negative 10, minus 1 is negative 11. And then in the denominator, we'd have negative 5 minus 4 is negative 9. The negatives are the only thing that we could reduce here, so we would have 11 ninths as the y value for our hole. All right, so that's where the hole would be. So now let's go back. Like I said, so those x plus 5s canceled out. So in our numerator, any factor that's left over in our numerator, that's where we get our x-intercepts from. We set that factor equal to 0 and solve it. Numerator, we just have 2x minus 1. So if I set that equal to 0 and solve it, I would get x equals 1/2. Or we could write that as, so again, this is not an asymptote, so we don't want to get confused by that. It's not an equation. So the x-intercept would be the point where x is 1/2 and y is 0. So that's your only x-intercept in this situation. All right, so now let's look at the y-intercept. So to find the y-intercepts, we're just going to replace every single x with a 0. So I like to go back, I think it's easiest, to be honest, to go back before we factored it. Before we factored it, if I replace all those x's with zeros, I'd be left with -5 in the numerator and -20 in the denominator. If we reduce that, we would get 1/4. So that means that my y-intercept would be the coordinate where x is 0 and y is 1/4. All right, so let's carry on now. We already did D for the holes in the graph, so now let's find the vertical asymptotes. So the vertical asymptote, that's what's left over in the denominator, our non-removable discontinuity, what x can't be. So here we would have the equation x equals 4. So that was easy enough. So to find any horizontal asymptotes, again, that's where we look back before we got it in factored form. So go back when it's in standard form. So this you must go back and look at when it's in standard form. So in standard form, the numerator, the leading term is 2x squared. The denominator is x squared. So the x squares cancel out, leaving us with 2. So this would be a, whoops. So this, if the variables cancel out, this is where you end up with, y equals 2 would be your horizontal asymptote. So when the variables cancel out, whatever's left over, ignore the bell, is your answer. So y equals 2 would be our horizontal asymptote for that problem. All right, so the last thing that they're asking for is to review the end behavior. So been a while since we've talked about end behavior, but anytime we have a horizontal asymptote, that's going to tell us what our end behavior is going to be. And I'll show you the graph here in a little bit so you can see how that works. But for this one, since we had a horizontal asymptote where y was 2, we would have a limit as x approaches negative infinity, so the left side of the graph, it would equal 2. And then we would have a limit as x approaches positive infinity so that'd be the right side of the graph, it would also equal 2. And again, I'll show you that with the graph here in just a little bit. But that's always going to be the case. Anytime we have a horizontal asymptote, whatever the horizontal asymptote is, that would be your limit. So for these problems, your limit will either be 0 or a particular value. And lastly, the domain is based on the holes in asymptote. It deals with the restrictions, what x can't be. So remember, x can't equal 4 and x can't equal -5. So it's based on those vertical asymptotes. So it can be everything else. So if we want to use a number line, you can. Let me do that. For some reason, this isn't erasing. There we go. All right, so if we had a number line, we'd have a gap, an asymptote at -5, and we'd have an asymptote at 4. But everything else would be included. So we would say from negative infinity to -5. Say from -5 to 4, and from 4 to infinity. That would be the domain of that polynomial. So before we're done with this video, I just want to show you now what the graph would in fact look like. So you can see that we would have a vertical asymptote at x equals 4. We see that we have a horizontal asymptote at y equals 2. We see our x-intercepts. Here's that hole where x is -5, y was 11/9. And if you look at the end behavior, so as we're approaching the left side of the graph you can see is approaching that horizontal asymptote at 2. And we can see the right side of the graph is also approaching that horizontal asymptote at 2. So I wanted to make sure that you see that and you can recognize then what the significance of those horizontal asymptotes are in regards to the end behavior. So we're actually going to stop there with this video. So good luck now as you work on your assignment.